In section 5.6, we will talk about rational functions and analyzing the graphs of rational functions. To begin with, a function of the form f of x equals p of x over q of x, where p of x and q of x are both polynomials with q of x not equal to 0, is a rational function. Notice that q of x cannot be 0 since we cannot divide by 0. Here's an example. Let's take a graph of f of x equals to 1 over x minus 3, which is in the form of p of x over q of x, making that a rational function, and graph that on Desmos. So I graphed it on Desmos, and this is what the graph looks like. Now the question is, what happens to the function f of x as the values of x approach x equals to 3? Okay, so let's take a look. So this is x equals 1, x equals 2, x equals 3. The graph is going to go get very, very, very close to this line right there, x equals 3. So I'm going to, let me highlight that line. Okay, so that graph is going to get very, very close to this line, x equals to 3, without actually touching it. Same thing on the other side. As x approaches, this is 5, this is 4, this is 3. As x approaches 3 from positive infinity, so the graph is going to get very, 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 very close to that line x equals to 3 without actually touching or crossing it. So the vertical asymptote of a graph is a vertical line x equals a, where the graph tends towards positive or negative infinity as the inputs approach a. In other words, as x approaches 3, then the graph f of x will approach negative infinity. As x approaches 3 from the positive side, the graph of f of x will approach positive infinity. So as x approaches a, f of x approaches infinity or negative infinity, making that a vertical asymptote. Now let's take a look at what happens to x, or what happens to the graph f of x as x approaches infinity and negative infinity. And let me use a different color for that. So, sorry. So as x approaches positive infinity, look at the graph. It's going to get very, 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 very close to this line, the x-axis, without actually touching it. Same thing on the other side. As x approaches negative infinity, the graph is going to get very, 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 very close to that x-axis without actually touching it. So the x-axis in this case, this is called the horizontal asymptote. And the line x equals to 3, this is called the vertical asymptote. So the horizontal asymptote is a line y equals b that the function approaches as x approaches positive or negative infinity. Now notice that the graph of any vertical line has an equation of x equals to something. So in this case, it's x equals to 3. The equation of any horizontal line will always be in the form of y equals to something. So in this case, this is like y equals 1. So this is y equals 0. So the x-axis has the equation of y equals to 0. In this section, we are going to talk about how to find these horizontal and vertical asymptotes. So there are a bunch of rules here. We have 5 different steps on analyzing the graph of a function. I'll let you can pause this, you can read them, but we'll go over them one at a time as we do these problems. And what I recommend for your exam is that you follow these exact 5 steps. So let's take a look at our example. We have f of x equals to x squared minus 4 over x squared minus 2x minus 8. And step 1, we want to factor the numerator and denominator. Okay, so, and I'm just going to go step by step. I'm not going to skip ahead. So step 1, let's factor the numerator and denominator. So the numerator, it's x squared minus 4. That's a difference of 2 squares. If I factor that, that's going to be x plus 2 times x minus 2. My denominator, I need to find two numbers which multiply to be negative 8 and add up to be negative 2. And those are going to be x minus 4 and x plus 2. So we did step 1, which is to factor the numerator and denominator. Step 2 says, find the domain of the function. Now remember that because we cannot divide by 0, the denominator q of x can't be 0. In any rational function, the restriction on the domain is that the denominator cannot equal to 0. So let's find our restrictions on the domain. Okay, so part A, we're going to factor f of x. I'll write that in factored form. That's equal to x plus 2 times x minus 2 divided by x minus 4 times x plus 2. Part B says find the domain of f of x in interval notation. So the domain of f of x, the denominator cannot be 0, and that's a restriction on the domain. So we're going to have our denominator, which is x minus 4 times x plus 2, and that cannot equal to 0, which means x cannot equal to 4, and x cannot equal to negative 2. Before we can write this in interval notation, I'm going to graph these on a number line. So here we have negative infinity, here we have infinity. X cannot be 4, x cannot be negative 2. So at negative 2, we have a hole, and at 4, we have a hole. And what that does is that the graph gets split up into different parts. We have the first part here, then we have the second part here, and then we have the third part here. So in interval notation, this first part can be written as negative infinity, comma, negative 2. Notice we have a parentheses on negative 2 since negative 2 is not included. Union, we have the set of numbers between negative 2 and positive 4. Union, the set of numbers between 4 and infinity. So that is our domain. And that's just another, in interval notation, that's just a way of saying that our solution set can contain any values except for negative 2 and 4, because those values will give you a 0 denominator, and that will give us an undefined answer. Okay, so that is part B. Now let us go to part C. Find any vertical asymptotes and holes. So how do we do that? Let's take a look. Part C. To find the vertical asymptotes, if x minus r is a factor of only the denominator, then x equals r is a vertical asymptote. If x minus r is a factor of both the numerator and denominator, then the graph will have a hole at x equals to r. Now, what does that mean? Let's take a look at our factors. And here we're specifically looking at the factors of the denominator. So to find the vertical asymptotes, we're going to focus on the denominator, which is x minus 4 and x plus 2. Now, x minus 4, it's only a factor of the denominator. And let me write that down. X minus 4 is only a factor of the denominator. If x minus 4 is only a factor of the denominator, that means we are going to have a vertical asymptote at, if I set x minus 4 equal to 0 and solve for x, I get x equals to 4. So I'm going to have a vertical asymptote at the line x equals to 4. So vertical asymptotes are determined by the factors of the denominator. And if a factor of a denominator, it's only a factor of the denominator, then you have a vertical asymptote. Well, let's take a look at x plus 2. X plus 2, it's a factor of both the numerator and denominator. In other words, if I were to simplify this, the x plus 2 and x plus 2 will reduce. They will divide to be 1. So when you have a factor that's a factor of the denominator and the numerator, that means you are going to get a hole at that point. Okay, so x plus 2 is a factor of both the numerator and denominator. So when an expression is a factor of both the numerator and denominator, there's going to be a hole at that point. So we will have a hole. And remember, we're always setting this equal to 0. So if I set x plus 2 equal to 0, then I get x equals to negative 2. So there's going to be a hole at x equals to negative 2. Okay, so we're working through this step by step. Part D, find any horizontal asymptotes. So for that, n is a degree of the numerator and m is a degree of the denominator. So degree of the numerator is 2, degree is the highest exponent, and the degree of the denominator is also 2. We also have to identify a and b. A and b are the leading coefficients of the numerator and denominator. Leading coefficients are the coefficients of the highest degree. So in this case, a is going to be 1, and b is also going to be 1. So a and b are both 1. Now let's read the rules. If n is equal to m, which means if the degree of the numerator is equal to the degree of the denominator, which is what we have, then we have a horizontal asymptote at y equals to a over b, where a and b are the coefficients of the numerator and denominator. So a is 1, b is 1, the degrees are equal. So when the degrees are equal, then we're going to get this case where the horizontal asymptote is going to be the line y equals to a over b, a is 1, b is 1, which means y equals to 1. That is going to be our horizontal asymptote. Okay, so that's part D. Um, the next one, it says, in order to find the x-intercept and y-intercept, first write r in reduced form, which means cross out any common terms on the numerator and denominator. So on the numerator and denominator, we have a common term of x plus 2, which is where there's a hole. So that is going to be our common term, which I've crossed out. Now, once I cross it out, um, I'm going to write the simplified form right up here. Okay, so the simplified form is this. The simplified form is f of x equals to x minus 2 over x minus 4. Because remember, the x plus 2's, we cross those out. Now, how do we find the intercepts of f of x? Let's take a look. To find the x-intercept, set f of x equal to 0 and solve for x. To find the y-intercept, set x equal to 0 and solve for y. Okay, so let's do this one at a time. And I know I'm kind of running out of space, so forgive me. To find the x-intercept, we are going to set the whole f of x, which is the entire left-hand side, equal to 0, and solve for x. Okay, so to find the x-intercept, we're going to set f of x equal to 0 and solve for x. So this whole left-hand side is going to be 0, which means we're going to get 0 equals to x minus 2 over x minus 4. And then we are going to multiply both sides by x minus 4 because you want to solve for x. There's an x minus 4 on the denominator, which we don't want. So I'm going to multiply both sides by x minus 4. So these are going to cross out. And then we know that 0 times anything is going to be 0. So I'm going to keep going over here. We're going to have x minus 4 times 0, which is 0, and that equals to x minus 2. And now if I solve for x, by adding 2 to both sides, I'm going to get that x equals to 2. So my x-intercept is going to be x equals 2, and the ordered pair is going to be 2, 0. That is my x-intercept. Okay, and again, I know I'm running out of space, so I'm going to try to squeeze this in here. To find the y-intercept, let's take a look what it says. To find the y-intercept, set x equal to 0 and solve for y. So basically, I'm looking for what is f of 0. I want the x value or the input to be equal to 0. So if I plug that in, I'm going to get 0 minus 2 over 0 minus 4. That gives me a negative 2 over negative 4, which is going to be 1/2. So my y-intercept is going to be the point 0, 1/2. So my y-intercept is a point 0, 1/2. Now, lastly, we're going to sketch this graph by labeling all asymptotes and intercepts. So let's start with part C, which is find the vertical asymptote. The vertical asymptote we said is x equals to 4. So at x equals to 4, I am going to draw a vertical asymptote. We have a hole at x equals to negative 2. So at x equals to negative 2, we're going to get a hole, but we don't know what the graph looks like, so we're going to leave that alone for now. The horizontal asymptote is going to be the line y equals to 1. So at y equals 1, I'm going to get a horizontal asymptote. My x-intercept is 2, 0, which is here. My y-intercept is going to be 0, 1/2, which is going to be there somewhere. Now we know that the graph is going to approach these asymptotes in each direction. So when I sketch the graph, it's going to go like this. It's going to have this kind of behavior. And then same thing on this side, it's going to have this kind of behavior because these are asymptotes. So the graph is going to get very close to them without actually touching them. And that's going to be the sketch of a graph.